Okay. A definition here, we're going to say that a complex series, so a complex series a sub n, so here our a sub n's are complex numbers, is going to converge absolutely. So this converges absolutely if the sum of the modulus of the terms converges. Okay, so if the sum of the modulus of the terms converges. Now, this is going to be, of course, absolute convergence and conditional convergence and divergence is a topic that gets talked about in calculus. But anyways, so this is a notation that we're going to use there. So that's absolute convergence. If you have, I want to prove this because this is not an obvious thing. I know that oftentimes what happens is that something gets discovered in math, it gets a certain name because it has certain characteristics. And then when we see the name, we just assume those characteristics, which is why it has that name, but this is not as obvious as you think it is. And if you think it's obvious, pause the video and try and prove it. Okay, prove that every absolutely convergent sequence converges. Okay, so yeah, it's not as obvious as you think it is. If you disagree with me, pause it, do it yourself, email me, and we can go from there. But what I was getting at, I need to write better because I didn't actually write the proposition, I just said it. Every absolutely convergent series converges. Again, that sounds obvious because the way that it's defined, it sounds like absolute convergence is a subset of convergence, which it is. That's why it's named what it is, but we can't assume these properties ahead of time. Okay, so I want to prove that this happens. This is not as obvious as we think it is. Now, if the values a sub n are real, then what we can do is just look at when is this positive, when is this negative. We can add those up and get the absolute value. So what we'll do is we'll define a sub I plus to be the value a sub I if a sub I is greater than or equal to 0, and it's going to be 0 otherwise. And likewise, a sub I minus is going to be the value a sub I if a sub I is negative, and it'll be 0 otherwise. Okay, so this is the kind of positive and negative parts of the function. And this is going to be useful for us because it turns out that the absolute value of a sub I, well, that's going to be a sub I plus minus a sub I minus, right? Because if hopefully that makes sense. If the term is negative, so first of all, if the term is positive, you just get a sub I because the absolute value of a sub I is just itself, and then this other part is negative and everything's fine. If a sub I is negative, then the absolute value of a sub I is going to be negative a sub I, in which case that's why we needed the negative sign there. So anyways, so this is the absolute value of a sub I. And then what we can do is we can look at the series. So since, what do I want to say here? Yeah, also, I'm sorry, I forgot one other statement here. A sub I is a sub I plus a sub I minus. Okay, so that's, I think, going to be relevant for us as well. Okay, so since this series, since a sub I, and again, I'm committing a cardinal sin here. I'm using I in a complex analysis course not to mean the number squared where that gives you -1. So if that bothers you, just change these all to j's, which I'll do now. It bothers me a little. So I don't know why I did it. But anyway, so since this series converges, then we can look at this a little bit and we can see what's going to happen. So since the series converges, then let's look at the sum of the positive parts, a sub n plus and the other one, a sub n minus. This will be very similar. So I want you to notice that, so this is what we're going to look at. And I want you to notice that if you were to look at these a sub n's, these are going to be greater than or equal to 0 by definition, and less than or equal to the absolute value of a sub n. Okay, and so that means that this series, a sub n plus, converges by the comparison test. So that converges by the comparison test or the comparison theorem, or however you want to say it. Okay, so that's going to converge. And by the way, I'm sorry, I don't mean the plus there, I mean a sub n. Well, the other one that I said was true, but that's, again, silly, because if a sub n is positive, then it's equal to its own absolute value. So this is still true if I delete that. So this series converges by the comparison test. The other series, so does this other series, the sum of a sub n minus. That also converges by the comparison test. And therefore, so does the sum of these two. So the sum of a sub n plus the sum of a sub n minus, which is really the sum of a sub n, converges to. Okay, and so that's how that works when you have a real valued sequence. And if a sub j is complex valued, then what you do is you break it up and you write it as b sub j plus I c sub j. And then you apply this theorem to the b sub j's and the cj's, and then everything is fine. Okay, so and apply what we did above to the b sub j's and the sum of the imaginary parts, cj's. Okay, and then the sum of the AJs will be exactly BJ plus I CJ, right, by definition. So then this, which is really the sum of the B sub j's as j goes from 1 to infinity, plus I times the sum of C sub j as j goes from 1 to infinity, converges. Because it'll be the sum of two convergent sums. Okay, so it's two convergent series being added. So that means that it's going to be a convergent sum. Okay, and so that's why if a series converges absolutely, then it converges.